Hey, this is Horner. We're going to look at our next topic in electrostatics, and this is called Coulombs Law, and this is section 16.3 in your book. Coulombs Law basically just gives electric force that acts between two different point charges. So I have two objects, two point-like objects, with non-zero electric charge. So this one might be 4 coulombs, and this one might be -3 coulombs. And we would find out what that force is between the two. So like gravity, the electric force is an inverse square law force. So if you remember the force due to gravity, Fg, that's equal to big G times the mass of the larger object times the mass of the smaller object, all divided by the distance between them squared. So we said that this is an inverse square law because it's proportional to 1 over r squared. The electric force, or the force we're going to look at that we're going to use Coulomb's law for, Fe, is also proportional to 1 over the distance between two objects squared. So it's also an inverse square law. And that's what they mean by inverse square law. Here's the equation for the Coulomb's law. This is force is equal to K times the absolute value. Notice that we're going to remove the direction on these. So this is K times the absolute value of Q1 times the absolute value of Q2. Remember, Q stands for charge, and that's divided by R squared, where K is a constant. We call it the Coulomb constant. And it can be written in terms of another constant, this E epsilon naught, and it's called the permittivity of free space. And it's basically just 1 over 4 times pi times k, and we end up with 8.85 times 10 to the 12th, and that would be the value for epsilon naught. So F is also equal to, so if you don't put the k in, you have to use this larger equation. It's just 1 over 4 pi times epsilon naught times r squared. That's the magnitude of the electric force. So we've got to figure out also the direction. So we know that we're using absolute value for the others. Now we've got to look to see kind of which way the direction is. If I have two charges, I've got a positive charge and a negative charge. And remember, we said that opposite charges, so if these are opposite, then they must attract. So opposite charges attract. Like charges will repel, and we see that these are both repelling. Notice that even though this charge is larger than this charge, the magnitude of the force, so the force of 1 on 2 and the force of 2 on 1, are exactly the same, and that's because of Newton's third law. So for every action, there's an equal and opposite reaction. Same thing with these. Notice that this one's a little bit bigger, but the forces are the same. Same thing here. This charge is a little bigger, but the forces are the same. So that'll be important as we go through and study Coulomb's law. Problem solving tips. We always want to make sure that we use consistent units. A lot of times we don't use just 1 coulomb. It's a very large value. Instead, we'll use microcoulombs, or we will use nanocoulombs. So make sure that if it's micro, you use 10 to the -6. If it's nano, you're using 10 to the -9th. So units are really important here. Let's see, when finding the electric force on a single charge due to 2 or more of the charges, find the force due to each of the charges separately. So if you have the 2, we've got 1 here and 1 here, we'll have to find the value for each one, and then we'll do the vector sum of the charges. You also will have it where they're going to be in different places, so you might have 3 charges that are like this, so you have both an x and a y, so we'll call this positive y, we'll call this direction positive x, and we would have to find the force between these two in both directions. That's a pretty easy thing to do. You've done that several times before in different units. For number 3, if I have a lot of different charges, there are some shielding, and so we'll kind of look at that as we do some examples. And it also says that the electric force is a long-range force just like gravity. So the gravitational force of Earth due to the sun does not stop when the moon passes between the two. That still is there, and so we'll have to kind of look at that as it goes through. Now we've got these 3-point charges. They're arranged in the arrangement you see below. They put them on a grid to help you a little bit. Charge Q1, this one has a charge of 1.2 microcoulombs. It's at the origin. The second charge Q2 is negative 0.6 microcoulombs, and our third charge here is 0.2 microcoulombs, and it's positive. They want to know what is the force on Q2. So what is the force on Q2 due to the other two charges? So we're going to look at how is Q3 affecting this charge and how is Q1 affecting the charge. And remember, you can't just go by distance. You also have to go by the magnitude of the charge also and see how those relate. So if we're going to solve this problem, the strategy that we'll use is to look at the force on Q2 due to Q1 and Q2 due to Q3. We'll do those separately. After sketching a free body diagram, we're going to add the forces as vectors, and then we're going to let the distance between the charges 1 and 2 be r12, and between r2 and 3 be r23. Okay, so the first thing we need to do is really go through, let's use these diagrams that we have in order to show some distances. So the first distance is from Q1 all the way up to Q2, and so that one R12, that's the one we don't know. That's the one we need to solve for. We do know the distance left to right, so the horizontal distance here is 1.2 meters. And then we know the distance from Q3 to Q2, and that would be 0.5 meters. So now we have our distances. I'm going to change pin size here and make it a little bit easier. I need to find R1, 2, and notice that we've made a really nice right triangle here. And so that should be equal to the square root of R13, R13 squared plus R23 squared. So here's our R13, here's our R23. You want to plug those numbers in, so this is equal to the square root of 1.2 squared plus 0.5 squared. And so we'll end up with this distance equal to 1.3 meters. So this one's also 1.3 meters. Okay, great. So now we know the distance between the charges of Q1 and Q2, and we can move on. So let's first find the force of charge 2 on charge 1. We're going to use Coulombs Law, so we're going to use K. I'm going to put Q1, Q2 all over R squared. And I'm not going to put in the absolute values, but we just want to assume that they're there. K, your book uses 8.99. I'm just going to use 9 times 10 to the 9th. And I'm going to take that times Q1, which is 1.2 times 10 to the negative 6th, times 0.6 times 10 to the negative 6th. And I'm going to divide that by that distance we just found, and that's 1.3 squared. That value ends up being 3.83 times 10 to the negative 3rd newtons. We also need to find the force of 3 on 2, so we're going to put F23 here. That's equal to, we know the equation already, so this is 9 times 10 to the 9th. Times, we're going to use 0.2 times 10 to the negative 6th, and that is times 0.6. So let's make sure we see that 0.6 times 10 to the negative 6th, and we're going to divide all that by 0.5 squared because that's the distance between them, and we end up with 4.32 times 10 to the negative 3rd newton. So now we know the force between 2 and 1, and we know the force between 2 and 3. So let's find the force between 2 and 1 in the x direction. And so we're going to really think about this triangle that we have here, but we want it in the x direction, so we only want it going left to right. So that's going to be equal to negative the force of 2 on 1 times the sine of the angle. And because we're finding this bottom part, we know that the angle is here, and so this would be the this is the opposite side, so we'll put OPP, and then this is the hypotenuse, which makes this the adjacent side of our triangle. We do know that sine is opposite over hypotenuse, and I already know what the opposite and the hypotenuse are. So what I'm going to do here is just say this is equal to negative 3.83 times 10 to the negative third, so that came from right here. So this is 2 and 1 on the x, and now we've got to do the sine of the angle. But we don't know what the angle is, but we do know opposite length and we do know hypotenuse length. So we're just going to take 1.2 and divide that by 1.3. And so your answer here is negative 3.53 times 10 to the negative third newtons. How about the force of 3 on 2 or 2 on 3 in the x direction? And we notice that this force is only going up and down, so there is no left or right component for it, so this is just 0 newtons. Now we need to do the same thing in the y direction, so force of 2 on 1 in the y direction, so that would be the component of this force, which would be straight up and down. And that would be adjacent to our angle. So this is F21y is equal to negative F21 times the cosine of the angle. We said that this was negative 3.83 times 10 to the negative third. And then we need to put in our positions or our distances here. This is 0.5. And then the bottom one is 1.3. So we've got this side, and then we've got our 1.3, which is this side. And once we do that, we end up with an answer of negative 1.47 times 10 to the negative third newtons. The other thing we need to do is find out what is the force between 2 and 3 in the y direction. And because that's the only direction, we can just write down what that magnitude was and the direction. So this would be negative 4.32 times 10 to the negative third newtons. All right, so now that we've done those things, we need to go back and we need to find out what is now the force line number 2. So that's this right here, or it's this right here. We want to find out what is the combined force between the two. So to do that, we need to use the following. We're going to say this is equal to the square root of the sum of the forces in the x direction. So we need to add the two x directions together. There's only one in the y. Well, there's only one in the x direction. There are two in the x in this direction because we had one for each one of the two components. So here we've got sum of the forces in the x squared plus sum of the forces in the y squared. We'll go ahead and plug our numbers in. So sum of the forces in the x, there's only one force in the x, and that's 3.53 times 10 to the negative third, and it is negative. Won't matter in the end since we're squaring it, but we'll put it there. Plus, now we need to add this number and this number together. And when you add those two numbers together, you get negative 5.79 times 10 to the negative third squared. If you do all that math, you should end up with a value of 6.8 times 10 to the negative third newtons. Okay, so that would be the force along this line, would be 6.8 times 10 to the negative third newtons. Now, the last thing that they want us to do is they want us to find out what is this angle right here. And we can find the angle using the two sides that we already found down on this part. So the sum of the forces in the x we said was 3.53 times 10 to the negative third. And along the y was 5.79 times 10 to the negative third. What I'm going to need to do is just get rid of this little guy right here for just a second so that we can find our angle, and I'll do it in red to make it a little bit easier. We're looking for phi here. So if I have these two sides, then what I can do is just say the tangent of the angle is equal to 3.53 times 10 to the negative third. That would be the opposite side over the adjacent side, which is 5.79 times 10 to the negative third. Then I'm going to do the inverse tangent of that. So I'll divide the two, do the inverse tangent, and I should end up with 31 degrees. You want to make sure that your calculator is in degrees and not in radians. And that is the end of 16.3 problem. Let's go on to the next part. Now we've got another problem. This is 16.4. We have a couple of styrofoam balls. They both have a mass of 10 grams. And they're suspended by threads. These threads are 25 centimeters long. We know that the angle is 15 degrees to the vertical for both of the sides. So they want to know, are the signs of the charges the same or opposite? They want to know, are the magnitudes of the charges necessarily the same? And then they want us to explain why. And then finally, they want us to find the net charge on each ball, assuming that the charges are equal. So if we think about our strategy, this is really similar to the electroscope. Each ball has an electric force since both of them are charged, and that's why they will push each other away. The gravitational on the balls are really, really small. Gravitational force is really small. If you remember the equation, F is equal to big G, and this is where I'm going to stop because big G has a very, very, very small value. In the order of times 10 to the negative 11th. If we do the force due to the electrical force here, force due to electricity, we know that that value is K, and that value is 9 times 10 to the 9th. So we've got a 10 to the negative 11th and a 10 to the negative 9th, so this force is really, really strong. The third force acting on the balls is due to the tension in the thread, so we can use a free body diagram in order to help us solve for that. So let's go ahead and take a look at part A. The electric force is clearly repulsive, so the charges must be the same sign. That's just the easiest way. There's no way to tell whether they're both positive or negative, so we're not really sure whether they're positive or negative. The force on either of the balls, so this was question B, is proportional to the product of the charge of the magnitude. So with Newton's third law, Coulombs law says that the two forces make up the interaction are equal and opposite. So the charges are not necessarily equal. They would not need to be equal. We just need to make sure that we always get that same force between the two. And that takes us to actually solving part C. All right, here we go with letter C. In letter C, we've got to find the forces in both directions. So we need to find the forces in the x direction and in the y direction. So let's start with the x direction. The sum of the forces, because this thing is not going anywhere, it's not accelerating, we're going to say that the sum of the forces in the x and the sum of the forces in the y are both 0. So what you might do is just say sum of the forces in the x are equal to 0. And then we need to figure out what are all the forces in the x direction. And let's go ahead and say that this is positive y and this is positive x. Positive y going up, positive x going to the right. Our force going to the right is the electric force, so we're going to write it first. And then we need to subtract off Tx. But we can't just use Tx. We need to figure out what is that in relation to our given, our tension up and to the left. So this line right here, the Tx, is the same as the top of the triangle here. So I've got a triangle. This would be the opposite side. And if it's opposite, it's got to be sine. So this is going to be T times the sine of the angle. For looking at everything in the y direction, our weight is going down. So remember, weight is really mg. That makes the calculations a lot easier if we use mg. So going up is ty, but we can't use ty. We've got to figure out what is ty equal to. Ty is this side of the triangle, so this is the adjacent side. So this is going to be t times the cosine of the angle, and we said that this one was equal to t times the sine of the angle. All right, so we've got t cosine of the angle minus mg is equal to 0. At this point, we can solve the top one for Fe. Fe would be equal to t times the sine of the angle, but we can also solve this equation for t. So this one's going to be t is equal to mg over cosine of the angle. So we've got t times the sine of the angle is equal to, now we've got t sine of the angle still. we said t on this bottom one is mg cosine of the angle, mg over cosine of the angle, so I've plugged that in. And sine over cosine is tangent. So now we know that FE can be equal to mg tangent of the angle. So now we don't need the tension anymore. Let's go ahead and use Coulombs law. So this is K. Now it's Q squared. It's not Q1, Q2 because both charges are the same. They've told us we can assume that. And then if I want to know what my distances are, I'm just going to take 2 times the length of this string here times the sine of the angle, which would be here. Okay, so it would be from here all the way over to here. So that would be 2 times that d times the sine of the angle, which would be this. And so you're finding one of these with just this equation. That would be that distance right there. And then I'm going to multiply it by 2 so I get the whole distance all the way across. If I solve this then for Q, it's going to be Q squared is equal to the electric force times that radius we just did, all divided by the constant K. So let's move on to the second part of the solution. Here is my Q again. We've got FE. We said FE was equal to mg tangent of the angle, so that's all that is. Oops, FE is equal to mg tangent of the angle. We said R was 2d sine of the angle. We've got to square it. That's all over K. We're going to simplify a little bit. We're going to multiply everything here. We're going to square everything on this side. So this would be 4. So the 2 becomes 4. The d becomes d squared. Sine squared. And then we take a look here. It looks like, yeah, so we've got sine squared of the angle. And that's all divided by k. So now we're going to go ahead and plug everything in, take the square root since this is q squared. So 4 times 0.25 meters squared was our distance. Remember, it was 0.25 meters times 0.01 kilograms, so that was the mass of the ball, times 9.8, which is the value for gravity, times tangent of 15 degrees times sine squared of 15 degrees. And all divided by 9 times 10 to the 9th. So you end up with an answer of 0.22 microcoulombs. And remember, we're not sure whether that's positive or negative because they both could be positive or both be negative. So we actually have either answer here would be appropriate. And that is the end of 16.4. Let's do some quick checks just to kind of make sure we're understanding the material. So we have the charge on sphere 2 is twice that of sphere 1, so we've got 2 positive charges instead of 1. It says which vector below shows the force of 2 on 1. So I know the force of 1 on 2. I need to find the force of 2 on 1. Remember, really important here to remember Newton's third law, and if you remember Newton's third law, you should come out with an arrow that looks exactly the same in magnitude but is opposite in direction. And so it would be the answer that you see here for letter B. It would be in this direction. It would be the same size, just in the opposite direction as the other force. For 20.8, this one says the charge 2 is twice that of sphere 1. Which vector below shows the force of 1 on 2 if the distance between the spheres is reduced to r over 2. So I want to know if I reduce this distance, what's going to happen? And my answer here is none of the above. Because if you look, if you measured the length of this arrow and you compare it to this one's only twice as long as this one. And if you remember, when you get closer, this is F is proportional to 1 over r squared. So if I half the distance, okay, so if I do 0.5 squared and do 1 over that, that force will be 4 times bigger. And so I would need to have an arrow that's 4 times larger than this one. So none of the above is the answer on that one. That was 20.8. Quick check. Let's look at 20.9. It says which of the 3 right-hand charges experiences the largest force. So here we've got just big Q and little q have the same magnitude and they're at a distance r. Now I've got double the distance and I have double the charge here. So remember, when we think about this proportionally, we do 1 over r squared, and then we do F is proportional to the product of the two charges. So we've got to go through and kind of figure out which answer this is. If we look at this one, we could say that because the R is 1, that makes this 1, and each one of these are 1. So our original force here is equal to 1 unit. Let's go ahead and check this one and see if it ends up being the same way. So this would be F is proportional to, and then I'm going to do Q1 times Q2, so that'd be 2Q times Q would be 2 over, and then I've got double the distance, so that would be 2 squared on the bottom, and that would be 2 over 4, which would be 1/2. So this cannot be the answer. If I then try this one, let's see what happens here. So now I've got force is proportional to, and this is equal to 4Q times Q would be 4 all over, and then our distance here is really 2 again, so that'd be 2 squared. Aha! This is 4 over 4, and that's equal to 1. So let's take a look and see what the answer is. It says Q and 4Q are tied. So here we've got Q and 4Q are tied. So Q and 4Q have the same amount of force. All right, that is the end of 20.9. So let's take a quick look at Quick Check 2010. It says, in each of the following cases, an identical small positive charge is placed at the black dot. So we're going to place a charge right here. Those charges are all the same. In which case is the force on the small charge the largest? So if we look, we want a small distance and we want the biggest force. So it looks like C would be our answer. And if we do a quick check, we will see that this one has the smallest distance between the two and the largest charge between the two. And so our answer is C. 2011, an identical small charge is placed at the black dot here, and it says that it is a positive charge. All right, they want to know in which case is the force on the small charge the largest, and all charges shown have an equal magnitude. So this is the same as this one, just in an opposite direction. So if we do this one, we'll see that A would give you it says in which case is the force on the small charge the largest. So A would have the biggest force between the two. It's because it's in between the two oppositely charged items. And so here the force is right here. There's a bigger force in between the two. Here the force is between the two. Here the force is between the two, but because they're the same, they're actually pushing out on each other. And so we don't really get an effect on this dot in the middle. So because these two are pulling in towards each other, there's a pretty big force on that middle dot. And that is 20.11. 20.12, it says the direction of the force on charge negative Q, so that's this one over here, is it's either up, down, left, right, or the force on negative Q is 0. And the answer for this one is it is to the right. Negative Q here is slightly closer to negative little q than positive Q is. And because of that, it will get pushed to the right slightly. So even though it's being attracted by this one, it's much further away. And so this won't really matter much. It's just the proximity to that charge. And that is 20.12. 20.13, it says in which direction of, what is the direction of the net force on the charge at the lower left? So they want us to pick A, B, C, and D. So we're looking for the net force here, and obviously it's going to be down to the left. And that should be our answer. And it is, because these forces are all pushing down. This one's pushing straight down, this one's pushing straight left. If I add those two, it would be going this direction, and this one's pushing it in that direction anyway. So that is the correct answer. In which direction of the net force, what is the direction of the net force on the charge at the top? So I have this charge. I know that these two charges are pushing each other away. So I've got a force going this way and this way. And then this charge is actually pulling this one in this direction, and this one's pulling in this direction. So if I took these two vectors, and they should be the same length here, and I added the two together so I make a parallelogram, you'll notice that D will have to be our correct answer because that should be the direction that we're pulling those charges in, and that would be correct. And that is 20.14. The next section we'll do is 16.4, the electric field.